Thanks for coming. So today we're continuing on last talk. So last time we discussed like the relationship between deterministic, randomized, and quantum query complexity. And we are left with like one relation between quantum and randomized query complexity with bounded error in particular. And last time we used the pointer technique to show like various separation. Actually, we only mentioned one, proved one, but we mentioned the other separations. However, that technique would not help us too much in this comparison, in particular the randomized versus quantum query complexity in the bounded error regime. So we have to take another approach, and the approach is sometimes referred to as the cheat sheet method introduced.
Are you going to remind what quantum query complexity is versus? I think it would be good to do just a quick reminder of what the notions.
Wait, okay, let me see. So today I think our goal is to show the theorem that there exists some function whose randomized query complexity is quantum query complexity raised to the power of 3 for a total function. The randomized query complexity is basically that you have distribution on decision trees, and you want to be able to output like the correct answer of your function f with probability at least 2/3 on a random deterministic decision tree. Well, decision tree is deterministic, so on a random decision tree, so that's like randomized query complexity. And for the quantum query complexity, so you mentioned that you have like the quantum states, which is a vector, and initially it's normally the vector with only one entry, that is 1, meaning that you're at the states where all your inputs, all your quantum bits are initialized to be the 0 bit. And then during your computation, you're allowed to make queries and also do any computation. And a query corresponds to an operator that maps a query indices into -1 to the xi. So when you make query, you actually append this sign into your amplitudes. And when you do a computation, you can apply an arbitrary unitary operator independent of your input. So like a quantum algorithm, we're just quantum query algorithm, we just include a series of queries and computations like this. And the number of queries is just the number of the query operators you applied in your algorithm.
And in the end, what do you take? Just remind us, like the output of them.
So in the end, the output, what you do is you like measure the first quantum bit, which means that if you write down the final state, your output 1 is probability, which is a sum over all the amplitudes squared. The amplitudes are over the states whose first quantum bit corresponds to a 1.
Maybe I is not a good notion, is not a good like notation because it's not the same I as over there. There I
well, it is actually the same I.
Index.
It is actually a semi. So here, okay, let me write it down where Pt is just sum over the indices in the end of your code. Yeah. Okay. Hopefully this is good enough review for you. Maybe any questions? All right. So and we also mentioned okay. So in the last time we also mentioned that the largest possible separation for total function is quartic, is a power of force. That is due to Aronson, Van David, Kothari, and Tall, based on the result of Wang's sensitivity theorem. And this cubic separation are due to two independent work. One is Benso and Thingha. One is Rostov, Marchenko, and Wu. So that's me. Okay. And as I said, that to prove this cubic separation, we'll use a different approach. And the approach is this Chisholm method, first introduced by Aronson, Van David, and Kothari. It says that as long as you have a partial function, so partial function, I mean that a function that is not defined on the entire Boolean cube. So on some inputs, the output is not specified. Then in that case, your algorithm can take this advantage and output whatever you like. Anyway, so if you have a function, if you have a partial function, then there is a way to convert it into a total function. Whose input size is polynomially related to the original function. And in the new function, its quantum query complexity is something like small n, little n times the quantum query complexity of your partial function. And the randomized query complexity of the new function is at least n squared times the randomized query complexity of your original function. So that motivates us to look at the partial functions. And I think in the last time we looked at this huge problem. So the problem to distinguish whether your input has equal number of 0 and 1s or is completely just 0s and all 1s. So to distinguish these two cases, and I said that the quantum algorithm needs only one query, but the deterministic algorithm is like linear. So this is kind of like a very general thing for partial functions in the query model. For example, you can also exhibit similar things for randomized versus deterministic query complexity, and you can use the so-called gap majority function. So this function, it outputs 1 if your input has more than 2/3 ones, and it outputs 0 if it has less than 1/3 of ones. And for the case in the middle, we wouldn't care. So now clearly that in a random algorithm, you can just query a bit and query a random bit and output the value of that bit. It will give you a good enough probability to distinguish the 0 case and 1 case. But deterministically, you still need to query linear number of bits, right? Yes, okay. As for the case that we are really interested, that is quantum versus randomized in the bounded error regime. So actually we know there is exponential gap back in 90s due to Simon. It shows that there's some problem that can be solved using like polylogarithmic number of quantum queries, but classically, in particular, any randomized algorithm would require square root of n queries. And I also want to mention some like subsequent works. So first, the work of Ronson and Albinus. Like they improved on this separation, showing that there is problem whose quantum query complexity is 1, and randomized query complexity is order of square root of n. So not only exponential separation, but now we also have this constant versus polynomial separation. And then Tall, actually he worked on the problem, which is a generalization of the problem introduced by Ronson and Albinus. We will see that. So Tall showed that in this family of problems defined with respect to this parameter k, your quantum query algorithm can be like k over 2 for any integer k, and the randomized algorithm will be something like n to the 2/3 minus a small number, which is 1 by k. Okay, and you know, like in Bansa, Sinha, and Christoph et al.'s work, what happens is the lower bound was improved. So they gave a tight lower bound. Maybe use another color. Improving this to n to the one minus 1 over k.
These are not for partial functions, they're for full functions.
So they are for partial functions.
All of these are for partial. Okay.
Sure, yes. Yeah, so for total functions, it's impossible to have such separations because the largest possible separation is a partial.
Yeah. But I mean, big N there is, okay, so I'm missing something. Big N there is poly of little n. So
sure.
there is a plus. There is an additive plus. Okay, I see. Yeah, it doesn't give you like those sorts of. Okay.
Yeah. Wait.
Okay, maybe just comment on what you get for full functions.
Yes. So if you plug these results into this two-shift framework, and you immediately have a problem. It's total, and its quantum query complexity is something like k/2.
I think don't use this color.
Yeah, this color.
I'm pretty sure it's not. Yeah.
So which one is better?
There is a yellow on the right side. I see the yellow one. Like the far right, there is a yellow over there. Am I okay?
Okay. Let me try this one then. Hope it would be better.
It's like the white. Never mind.
Well, it is visible, but it's almost indistinguishable.
Maybe green. This one. Maybe this one. Anyway.
This is
bad.
This is the worst.
This is even worse than the.
Okay. Let's see. The red one.
People on the Zoom see the red.
The yellow is good. I can see the red, and the yellow is also good, and it's go from white.
The red is sorry. Yeah. My bad. You can go back to the red. Okay. Thanks, Ivan.
Great. Then we can use more colors. Okay. But let me. Okay. So what you do is you just plug in these separation results for partial function into the two-shift framework, and then you immediately see that there is total functions whose like quantum query complexity is constant times n, little n, and the randomized query complexity is n squared times n1 minus k. And you can take k to be large enough, to be a large enough constant. Then you get like n versus like n to the 2.99999. But actually, you can also take a k to be a little bit larger than constant, say log n. That is fine. Then you get this separation I wrote in the above. Okay. Any questions? And there is like one more thing that I would like to remark. I personally found it quite remarkable is that this like k/2 versus n to the 1 minus 1 over k separation is in fact the best possible we can get for partial functions, because we have like a simulation result. It says that if you have a quantum algorithm using a few number of queries, then you have classical algorithms uses like n to the 1 minus 1 by k queries. And this is due to Robbie, Morset, and Greer. It just says what it says. So if you have a quantum algorithm with k queries, k/2 queries, let's be aligned. then you also have a classic algorithm. So this classic algorithm will simulate the quantum algorithm. So if I simulate, I mean that the probability that this classical algorithm outputs a 1 will be close to the probability that your quantum algorithm outputs 1 of any input using the number of queries, which is k times like n to the 1 minus 1 over k. So, so these two bounds like matches. So it's kind of impressive that we not only have a very large separation, but we actually know like what is the largest possible separations for the partial functions. Okay. Well, if you don't have a question, then let me tell you what is the problem that exhibits this separation. So this problem is initially called a K-correlation. So the one that is studied by Aronson and Unbinus. And then it is generalized by Paul, and the new function has name raw relation. Maybe I'll tell you why it's called this name later. So the general case was first studied by Paul. To define this problem, we first has a parameter U, which is an orthogonal matrix. And with this parameter, we will have like k inputs, k strings. Each of length n. And the raw relation defined on these k strings is the following. So first you have this O1 vector of length n, and then you multiply on the left with a diagonal matrix whose diagonal is the vector xk. I should mean like, let me just write down what do I mean exactly. So the diagonal matrix is something like, actually -1 to like xk, the first entry, -1 to xk, the second entry, etc. So this -1 reflects your query operation. And then you apply U, the orthogonal matrix U, and apply the diagonal matrix whose diagonal is k-1 and so on. In the end, you would apply the diagonal matrix of B1. This way, you
with the all ones, not the identity. One is
this is
all
the
ones.
this is the O1 vector.
Ah, sorry, just the okay.
Yeah. So up to this point, you have vector, and you can just do a correlation. That's the relation in this name. You do a correlation. So take the inner product with another O1 vector, and you normalize it by taking by dividing n. So in this way, we defined a function whose range is actually -1 to 1. And then we can define the correlation problem. So the one instances are those whose correlation is large. Larger than 2 to the minus k, and zero instances are those whose correlation is smaller than 2 to the minus k minus 1, and the other inputs we don't care. I guess you can see that this problem is defined so that there is an efficient quantum query algorithm. And the algorithm is that you start from preparing this O1 vector, which corresponds to like the superposition of your query indices. And then you make a query to the last block of your inputs. And then you apply this orthogonal matrix, and then you query the second last block of your inputs. And in the end, after you like queried the first block of your inputs, you can take this projection, you project your quantum states into the space spanned by an O1 vector. So that's like what you do when you do a measure. So this immediately suggests a K query algorithm. And in fact, you can have a K by 2 query algorithm. So we just need to like rewrite this inner product. You know, you write the diagonal matrix, half of the diagonal matrix on the left and half of the diagonal matrix on the right. So on the left, you have like the O1 vector times the diagonal matrix of the first vector times the orthogonal matrix U times the diagonal matrix of the second vector, etc. Until the diagonal matrix of this K over 2 matrix. You take the inner product with, so that's the other parts of your diagonal matrix. And then in your quantum algorithm, you can actually prepare these two states in parallel. Yeah.
On a disjoint set of bits.
Yes, yes, yes. Yes. So you can actually prepare these two states in parallel. And what you kind of want to do is you want to take the correlation of two states, and it's kind of standard in quantum computing, and it's called like the swap test. I don't know why it's called that, but anyway, we have a quantum query algorithm using k/2 queries. And let me be a little bit more precise. The theorem exists A using K over two queries that outputs one with probability 1 plus the relation of function divided by 2. Yes. So comparing the output probability and the definition of our function, you realize that this algorithm will give us an advantage of 2 to the minus k, order of 2 to the minus k, to distinguish the 0 instances and the 1 instances. So basically it says that the quantum query complexity with respect to an error parameter a half minus 2 to the minus k is k over 2. So if you are really you really want to the error parameter, you really want the error parameter to be a third, you can do you can repeat your algorithm a few times.
So in the rest of the talk, there is not going to be any more quantum query complexity.
Yes.
Just the lower bound.
Yes, yes. Lower bound for classical queries. Yes. So it's basically about decision trees. Okay. Maybe any more questions? All right, then we'll go to the classical lower bound.
So this family of functions is basically tailor-made to be good for the quantum query complexity. Yes. Are all the bounds that you mentioned basically using this family of something like this, or you mentioned a sequence of works?
Right. But starting from Aronson and unbiased, then the final, right? Not like
not the one from the 90s, whatever that was.
No, right.
Okay.
Okay.
Okay. You wrote here. This is the AA.
Yes. And to prove this classical lower bound, we use a quite general framework. So let me tell you. So we start from the hard distribution, and in this case, we will have like two distributions, mu0 and mu1. That you should think under mu0 with high probability, the relation problem will give you 0. And for inputs from mu1, the relation problem will give you a 1 with high probability. So these distributions are different enough so that if you have a algorithm decision tree that computes the function with small error, can be used to distinguish these two distributions in the following sense. So evaluate your error on input sampled from mu0, then this expectation should be close to 0, and expect and evaluate your tree on input sampled from mu1, then this expectation should be close to 1. Therefore, the difference should be large. And if you want a quantity, actual bound, you can bound it as. Now, on the other hand, for shadow decision tree, we will show that this difference cannot be large. And we will use a Fourier analytic argument. So therefore, as a first step, we just apply the Fourier expansion to our tree T. So we will write it as summation Fourier coefficient times the difference between the expectations over the characters. And then for one of the distribution, we will choose the uniform distribution. So in our case,
maybe just define the Fourier transform of T. I mean,
okay, sure.
I guess most people have seen it, but
sure. So
let people.
Sure. Maybe. Okay. Let me write it here. Use a different color. So the Fourier transform, if you haven't seen it, it says that for any Boolean function, it can be written as like a sum of few components, so a linear combination of the character function, where the character function is a product. It's defined with respect to the set as the set. The index set, and where you have this set S, then the character of S is just the product of -1 raised to an input in this set. I guess maybe I also want to mention that if your function is like of bounded range, so let's say if T is 0 or 1 as its output, then how to say this? Then sum of Fourier coefficients squared is at most 1. Well, this is because
the characters form it.
Yeah, the characters forms an orthonormal basis for the space of the functions. Therefore, when you sum the coefficient squared in front of these bases, then you are just calculating the length of this vector, which is just, I didn't say like the inner product of this space. So the inner product of this space is to take the expectation of.
I think it's fine. I think.
Well, let me just say this is a fact without telling you why. Okay.
This is just Perceval, where you on the basis that's the Fourier basis. So this is just the fact.
Yes. Let me just write it as fact.
If you push it through this matrix whose columns are the characters, then this is an orthogonal matrix.
Mm-hmm. Well, okay. So for now, I just need to. I guess you just need to know that we are writing the ordinal function as a linear combination of base functions. So that's what we're doing here.
So what you wrote here is just what's written on the left board, right? Maybe just this out.
Just apply the Fourier expansion. Yes. So apply it. Okay.
Difference of expectations.
Equal. Okay. So now we have two distributions. For one of the distribution, we will pick the uniform distribution. This is because uniform distribution works really well when we take expectations over characters. As you can see, it's just the product of -1 to a variable. So if you are doing expectation over uniform distributions for, say, S that is not empty, then you always get 0, because like with half probability you get a -1, with half probability you get a 1. So you always get 0 for a non-empty character. And the empty character is constant. So these two constant terms were canceled out. So this really simplifies things. So we will write it as the weighted sum of the expectation of characters over this uncorrelated distribution. And the next, we just group the term based on the level of your Fourier spectrum. So take level from 1 to n, and within each level, just copy paste what's in the above line. Now, we want to decouple these two terms. There are various ways to do so, but here we take this option that we take the maximum of this expectation. So max and then we times the sum of this part. So so now, like, we have two separate tasks. The first one is we need to come up with a distribution that is different from the uniform distribution, and it has good behavior when you take expectation over characters. By good behavior, I mean that we hope that this quantity decays exponentially fast with respect to the size of the character, something like that. So decays fast. And on the other hand, on the left, we have this Fourier weight on decision trees. It has nothing to do with our problem now on the left part. So it has nothing to, it has nothing to do with the K correlation problem. And we wanted to grow slowly. So therefore, in total, this entire thing decays fast. And the sum will be small. Well, maybe any questions? Okay. So to come up with a distribution that is different from the uniform distribution and satisfies this good property is something delicate. So I will not discuss it in this talk due to the time, and we will focus on this clean part, which we only study the decision trees. So I want to emphasize that for this part, this distribution is completely given and analyzed by Hall. At that time, he already analyzed this part. Yes. So if
yeah, you can decide when is a good time for a 5-minute break. It's only 11:20.
Okay. Okay, but still, I think it's a good time to take like a 5-minute break here.
Okay, let's do it. It's very hard to describe the distribution.
It is a little bit difficult.
Even just to describe it.
Yes.
Okay. Is there like some?
So the thing is, uniform distribution will give you 0 with high probability. Well, of course, I guess. So this distribution has to be correlated, and the correlation will be decided by this orthogonal matrix U.
Mm-hmm.
Yeah.
And is there a general bound on the mass of the characters of a distribution that's being used? So maybe without telling us what the distribution itself is, there is some, general lemma that helps us give an upper bound for this maximum that is used, and you can just write what the, I don't know. I'm just.
I know what you're asking. So I think there is this. You probably know it. What is called isolisk theorem. What isolisk bound? I don't know.
Yeah, I can't actually see what you're writing. It's not on the camera.
Yeah. We're on a break, but like. Yeah. But yeah, you should write like since some people are listening.
Write on the backboard if you hold it for
now. No, I think there is some bound that if you want to like bound xi's for xi that is Gaussian, you can use xi. So actually this kind of distribution will come from Gaussians.
Sure.
Yeah, yes, not surprising. So there are like bound.
Gaussian chaos.
Yes,
blah,
yes.
blah. Okay.
Yes. Which I don't remember exactly. Like you come up with all possible matchings.
Yeah. Very nice. So these kind of things are used.
Yes. Also, you know this.
I mean, I know the Israel. Okay, yeah. Now I remember Disraelis or whatever, which is just an identity for those Gaussian.
Or independent.
Yeah. Okay. Yeah, I just wanted the flavor of what's going on in this bound.
So actually, like there's also I didn't mention it, but there is this parallel work of Benson and Singha. They didn't take the final step. They stopped at they stopped at here, and because this distribution comes from Gaussian, they took the approach of a stochastic calculus.
Say so. Okay, I think we have everyone there.
Okay. So now in the remainder of the talk, we just focus on this Fourier weight found on Deterministic trees. And let me just write down this bound first. So, okay. Before that, let me like specify some notation thing. So from the remainder of the talk, I think I'll be using the -1 and 1 representation for inputs, but the output you can still think it's 0 or 1. And in this way, when we write a function as a polynomial, then the coefficients of the corresponding monomial will just be the Fourier coefficient. But we will still stick to this f hat notation. And then we will study this norm, which is just the sum of the coefficient, the Fourier coefficient in absolute values. And then we also have this operator level L. So the level L Fourier spectrum of function f, or the degree L homogeneous part of a polynomial. Okay, with this set of notation, the theorem says that for any tree of strat D, then the Fourier weight level L is bounded by order of square root of D choose L, then log n to the L minus 1. And maybe let me make a few comments. So first, the range, it can be actually, it can be like a bounded range, say minus 100 to 100. That doesn't matter, similar bound will hold. And second, so in reality, we need to keep track of the density of our tree. So by density, I mean the probability that a uniformly random input has a non-zero output. Now the reason is basically because when we apply induction, the leaves labeled by 1 will be distributed to different subtrees. We will see in the later parts. So it's important for us to keep track of the density of the tree. And when you keep track of the density, then the bound should depend on the density. But this dependence is quite complicated that I don't really want to say what it is. But I guess maybe a good approximation for like large P. For large P, it is something like P times square root of ln E over P times ln En raised to the power of F. So for large P, this function behaves something like this. Can you see it?
Yeah, but what is this lambda?
Oh, so sorry, I didn't say P is the density of. Here, P is the density of the tree. Yeah. So I'm saying that because we are keeping track of the density of the tree, then this bound must depend on the density of the tree.
When there's a function that could behave like the right part.
Yes.
Ah, okay. Maybe use the blue instead of the red. From now, don't erase it, but from now on.
Okay. Okay.
Okay.
Yeah. So So dependence is quite complicated. It's segmented function. But to give you some flavor, it's something like this when p is large. Well, actually L minus 1. So like if you plug p equals to 1 into this formula, then it kind of reflects the bound here. Okay. And now this is, at this point, this bound may look weird. So let me give you some examples. And then you will like have some intuition about this bound and this problem as well. So we'll look at some simple example first. The first example, we just look at the unadaptive decision tree, by which I mean, in this decision tree, you always query the first bit in the beginning, and then whatever you get, you always query the second bit. And then you always query the third bit. So for such function, like only d variables will affect your inputs, will affect your output. Therefore, you can bound its level L Fourier weight like in the most straightforward way. You just write down the Fourier coefficient that we know cannot be 0. So there are at most like d choose L, such coefficient. And by this, you already know it's upper bounded by d choose L. But then we can also apply Cauchy-Schwarz. So that gives us like the number of non-zero coefficients times sum of the Fourier coefficient squared, which is at most 1. So this is square root of d choose L. So like the square root of d choose L showed up in the above bound. And then maybe you're thinking that, so in this example, because all the variables are like aligned in this manner, there will be a lot of cancellations. So therefore, the bound is small.
Just a remark, if you know also something about the density, it also gives you an even better bound about the L2 norm. So you can do a bit better.
Yes, yes, yes.
You can put here like a root of the density times 1 minus the density or whatever. So you already see some
just the
dependence
density,
on
right?
the density.
Yeah.
Just
the density, right? But okay. But I think that we don't need to do this.
Yeah, just a remark.
Yeah. Okay. Let's don't do this because now I just want to compare this bound with the first kind of bound without taking density into account. So, okay, so in the second example, let's just modify the first example a little bit. So in the first d-1 layers, we do exactly the same. We just query unadaptively, but in the last layer, in the bottom layer, we have distinct variables. And the output will be will depend on the value of the variables in the bottom.
Like the address function.
Yes, so exactly, yes. So this is exactly the address function. Maybe I'll write it down. Yes. And then we can write down its formula explicitly. This is a easy enough example. So, so for this t, let me just write it. Because we are using the -1, representation. So it looks like this. We are summing over all possible passes that leads to a y variable. And then we write down this indicator function that indicates the x variable will actually lead to this y variable, which would look like this. And then if you expand the out, you realize that for each leaf, for each y, there are like d -1 choose L -1s to choose the x variables. And each will have like its coefficients 2 to the -d+1 times a half. So that's 2 to the -d. And there are in total like 2 to the d-1 ways to choose the y. So anyway, the level L weight of such tree will be like half times d-1 choose L-1. Any questions? So this is this a counterexample to our bound?
What is the log business here? Yeah.
Yes, exactly. So so in this example, we have the number of variables exponential in the depths. So therefore, we can actually write this as something like square root of d choose L times like log n raised to the power of L-2.
Wow, so exactly.
Well, so here is L-2. And in fact, if you replace like a y0 by the majority gadget, then you will get L-1. So anyway, so this example shows that we need some dependence on log n if you really want the square root dependence over d choose L.
So the square root is going to be crucial in the steps that we're not going to see.
Right.
If you only got the d choose L without square root, it's much easier to get, but it's not going to help.
Right. So like in the
yeah, of course. Like without the square root, it's okay. Sorry. Then yeah, I didn't notice. It's just a trivial bound.
It is a trivial bound, yes.
Okay.
I don't know, maybe not that trivial, but
I mean maybe not with the like part about the density, but like okay.
Yeah.
No, I think it's completely
like n choose L is the trivial one.
Yeah.
Choose L is relatively
it's not clear. Yeah, sure.
It's relatively easy, but it may not be that trivial.
Yeah.
But it's still easy, fairly easy to verify. It's very easy to verify.
D choose L.
Yeah, D choose L, yes.
Is there like a hint you can give us just to see what it's?
Well, you just focus on each leaf basically. For each leaf, you only have like D choose L characters, and they contribute basically the same amount, which is 2 to the minus D.
Okay, right.
Okay. So basically, we showed that there must be some dependence on log n if you stick with the square root of D choose L in the beginning. And actually, this dependence on log n is tight. It has to be like log n to the L minus 1, because if you replace this y with the majority gadget, you will show that. So I think that's all I want to say about the examples. It probably give you some ideas about this bound and about this problem in general.
So this is a good point. What you just said, that like the calculation for the adverse function that gave you the D choose L is also an upper bound for every function by essentially what you wrote. Like
Yes. Yes. And this would be a perspective we take back during the entire proof, I guess. But I will emphasize that later. So now let's look at the level 1 case. So this, in this case, is actually studied by O'Donnell and Servidia, like back in 16. But they didn't like
you said 16 and you wrote 6.
Oh, okay. I mean 06. But they don't need to consider the density of the tree. Their application is to learn monotone decision trees. And for monotone decision trees, the sum of the level 1 Fourier coefficient is just the influence. Yes. So the general case was studied by Tall first. By general, I mean with the parameter of density. But the idea is essentially the same. So the key thing is that if you have decision tree T and you want to look at its level 1 weight, which is the sum of absolute values of like T hat I. And then I claim that you can actually discard these absolute values. It suffices to look at the functions, it suffices to look at the sum of the Fourier coefficient at the first level. Because if for some I, if the Fourier coefficient is negative, you can just come up with another function that negate xi. And this will not affect the depth of your decision tree. In your decision tree, when for T prime, what you do is basically you switch the left child and right child of the decision tree, of the original decision tree, if the node is xi. And once you have this observation, then what you need to do is just to maximize, find a tree that maximizes the sum of the Fourier coefficient at the first level. And we just write down the definition for the Fourier coefficient, which is expectation of a original function with our variable xi. Expectation over the uniformly random inputs. But because we have this decision tree, we can also first sample a subcube specified by a leaf. So that is sample leaf, and then sample input inside that subcube. But in that case, say if you sampled the subcube specified by this leaf, then for variables that is not queried along this path, then they would not affect the output. So they are like uncorrelated with your output. They are irrelevant, they contribute nothing. And for the variables that is queried. They contribute little, not nothing. No, that's not.
Sorry. Yeah.
If you restrict to do this subcube.
Yeah.
Okay, and if you look at the variables queried along this path, then they are fixed. And they are fixed exactly by this path. So let's call this path -1, 1 to the d. So this specifies the outcome of the variables you queried. Then you can actually express it as the label of this leaf. So let's use the notation PV times sum of VI. Okay. Yeah, once you write down this formula, you're basically done, because you realize that to maximize the level 1 Fourier weight, what you need to do is you need to put the ones on the leaves that is aligned with those whose root to leaf path contains a lot of ones. So all the calculations are mechanical, so I will not do them. I'll just write down what it is. So for any decision tree of density, its level 1 Fourier weight is upper bounded by some constant times p times square root of the depth of your tree and ln your p. Okay, I erased. Okay, so this will be the inductive basis that we use in the remainder of the proof. We will make induction on level, on L.
Okay, so in particular, if you know nothing about P, you just get root D, which is just
majority function. So the extremal case will be like this kind of threshold function. Any question?
And actually, for any P, it's like, yeah, exactly. It's like not majority, but like a different threshold.
Yes.
Whatever you call that.
Yes. Okay. Well, then let's move on. So when we look at like high level, then maybe let us first fix some notation issue and make sure that we are on the same page when I write something. So now let's say we have the tree, and I think we already used like this string of length b to denote a path, a root to leaf path. So this string can be used to denote a leaf as well. And in general, if you have a string of length at most d, then it can be used to denote any node on your tree. So for example, we can use the empty string to denote the root of our tree. And then let's use the subscript TV to denote the label of the V, of the node V on your tree. When V is a leaf, that is just what you are going to output on this student tree when you reach this leaf. When V is an internal node, then this will be the index of the variable that you want to query. And we were also, I think it's probably a bad choice of notation, but we'll also use subscript V to denote the subtree rooted at V. And then as I mentioned that, we really want to stick to this perspective that we express our tree as a sum of the subcubes of the subcubes. I'll say it. So we want to write down our tree as the sum of the leaves. And when you reach this leaf, you output the label on the leaf. Then you should have an indicator function indicating that you actually reached this leaf. So it would be something look like the thing. And then we will expand it out. You write it down.
Xi, it's X sub. It's not very.
Oh yeah.
T
less than B less than yes. Thanks for pointing this out. Okay. And when we expand this out, what we're doing is we are selecting the subset of layers. And look at the variables on the selected layers, and the coefficient in front will be like 2 to the minus d vs times the variables on the selected layers of this path. So I want to mention this is because I will be talking about like the contribution to the Fourier way by a set of nodes. And when I say that, it has a precise meaning, which is just TV times 2 to the minus d times vs. So contribution by nodes. So with respect to a path V and the set of layers, that is just, you don't really need to remember what is this exactly?
Sub S, it's not like exactly defined. But you really want like the product of the values of.
Yes, you're saying. Wait, what?
What? Just what is V sub S?
Yes, yeah,
It's
okay.
it's not all the entries of the vector, it's their product.
Yes. Okay. Okay. Now for the level 2 case, what we want to do is we want to like collect all the contribution by collect the contributions by all pairs of nodes. Yes. And then there is, I guess, a natural way to do it. That is, you fix some xi, say x1, so fix a variable. And then let's just focus on the contribution from the pairs formed by taking x1 and a node above x1. So once we have this kind of language, then it immediately implies we should have a tree that you cut off all the passes that does not lead to x1, and only keep those passes that lead to x1. And then for any subtree under node by labeled by x1, we don't really care about the structure of this subtree. What we really care about is just the parts involving x1. Well, in particular, in the end, what we actually care about is the Fourier coefficient of the function computed by this subtree for variable x1. So therefore, you can just replace this node with this Fourier coefficient. I didn't like say exactly why this is the case, but you can verify it.
Maybe you can just say it like this. If you already know the value of x1, then you only care about the average with respect to whatever comes next.
Yes.
Right.
Yes.
So it's really like you only care about the. Okay.
Yes. Sure. Yeah. Okay.
So it's just the difference between two averages, one where x1 is 1 and one where x1 is 0, which is exactly the Fourier coefficient.
Yes.
Like 1.
Yes, of the subtree for x1. Yes. Thanks for the comment. Yeah. So the point here is that now you have a tree whose leaves are labeled by some numbers, and you can write down the trees like for other variables, say x2. And that will recover like the contribution of from all pairs of nodes. Right, because here we are only like counting contributions from pairs formed by taking x1 and a node above it. And here we are counting the contributions from pairs contributed from x2 and node above it. And when you write down like n such trees, so a tree for each variable, then you will be able to compute the contributions from all pairs. And for each tree, you can replace the node, like labeled by the variable you're interested with a node that is labeled by a real number. That will not be an issue for us. So the point is that now you have a decision tree which you can actually apply the inductive hypothesis. So this is just the natural approach, and it will not give you the best upper bound. So instead, we were like set back.
Just so what will it give? Like how
yes,
will
so
be off by what?
So this will give you something like d to the L, d raised to the L, maybe some log factor. So like for constant L, this is fine, but for large L, it will be problematic. Like d choose d is 1, but d raised to power of d is huge, can be huge.
Yeah, so only when L is like really close to d. Like, okay. This is relevant for us.
Yes, but this is relevant for us, yes.
Yeah, I guess, okay, the values of L that are interesting are like L close to D, I guess.
Yeah, you can also compare this with the bound d choose L. So like when L is greater than square root of d, then this bound becomes bad.
Already, okay, yeah. It's pretty delicate, all this business.
Yes. Okay. So in our approach, we were set back a little bit and be less ambitious. So we were cut our trees into halves, and instead of collect like all pairs, we just collect the pairs by taking one node in the upper half and one node in the lower half. So in this way, we will underestimate the 408 because, for example, if the two nodes are both in the first half, then we're not counting it. But this is okay because then we can just consider another case where we pick a node from the first quarter and a node from the second quarter. So in general, so the really most general case when L is not 2 but L, we might want to consider like there are blocks of your trees, and we compute the contribution by taking a node from each block. So basically, what we need to do is we try to find a way of picking these blocks so that, how to say this? So we're trying to like find a lot of blocks. Like when we put them together, they will actually cover all possible ways of choosing error nodes. So that will cover all the contributions.
So just like as a general, I don't know, thumb rule, we're okay with losing any function of L that doesn't depend on D, essentially. Like that's almost true, but
yes,
right?
You're
we
right.
don't care about, okay.
You're right.
This is why we can we're free to play with all these types of configurations that only depend on L and not on D.
Yes, yes.
Maybe they depend on log D.
They will depend on, yes.
Because you need several scales.
Yes.
Okay.
Yes, but anyway, so the point is that by picking these intervals carefully, you can actually find an efficient way to cover like all the contribution of the set of size L. And maybe if so I think if you are fine with an upper bound that suffers from a logarithmical so that is logarithmically worse, then this is actually quite straightforward. But if you want to get the optimal upper bound, then you need to do some extra work.
And it's going to matter for the end result.
Sorry?
It is going to matter for the end result, like this logarithmic.
Yes. No, logarithmic won't matter. But if you want, so for the query complexity application, the logarithmic loss is fine. Yes.
Okay.
Yes. Yes. So anyway, so I want to focus on the part where we only compute the contribution from a pair of nodes that is one on the upper half, one is on the lower half. And the other issues I let us do not talk during this talk because of time. Okay, so what is good about this approach is that when we only care about the contribution from pairs with only one on the lower level, then so again, what we really cares about for a subtree in the lower layer is not its structure, but its linear parts. So let's just say that it is fine that you contract any subtree into a leaf that is labeled by the linear parts of the function computed by this subtree. And we don't like this tree that has its leaf labeled by a polynomial. So next, what we were trying to do is we are trying to like express such tree as a sum of trees where each of its leaf is just labeled by a single variable, possibly with a sign. And we can do this. I guess I can just show you an example. It will be quite clear that this applies to the general case. So let's say our tree has this node and that node. This node is say 0.1, x1 plus 0.9 x2, and the second knot, the linear function is just like 0.2 x2 plus 0.8 x3. And then you can just write it as like 0.1. For the first knot, you take this x1. For the second knot, you take an arbitrary variable x2. And then you add the 0.1 again, like x2 in the second knot, and and x2 also in the first knot. And then, oh yes. And then point A, what's remains? So x2 on the first knot and x3 on the second knot. So anyway, the point is that you can do it, and in addition, sum of AI is at most maximum of all the leaves over the level 1408 of the tree, of the subtree U. So this is because the coefficients just comes from the linear part, and its weight is at most. Yeah. Okay. So now let me make a comment. So if we how to say this? So now if the density of our tree is P, then the expected density of the subtree is also P. So the expectation of the density is just the density of the original tree. And let's just consider two extremal cases. The first case is when all the subtree has the same density, so same as the original tree. And after we apply this series of changes, then we end up in this tree. This tree will have maximum density. On the other extremal case, when a lot of trees has full density, a lot of subtrees has full density, but the other subtree has zero density. And then when we end up in this step, this tree will has density P. So there is this conflict between the density of the upper tree and the density of the lower tree, which will be crucial. For simplicity, let's just assume the density of all the subtree are the same. So they are the density of the original tree.
But isn't the function of the dependence on the density that you're trying to achieve is like a convex function of the density. So it's only helping you if you have some big and some small.
It's concave.
Concave, sorry. So I think it's going on the good direction, so that like you'll be able to.
But just by concavity, we couldn't do it. So it's not just about concavity.
Okay. Okay. I'm obviously missing something, but it's somehow important.
Yeah. But so okay. So I think for us, I think the important part is because of this. There is this interaction between the upper part and the lower part. So I can't say it's just about concavity, like on a single bound. Well, anyway, let's just focus on this special case when all the subtree has the same density. it will be a good illustrative example. So in that case, we know that sum of AI is bounded by what we wrote, p times d by 2. So we just plug in our base case. And then for this tree, so for a tree, let's just focus on a tree whose leaves are labeled by single variables. I think what we will do is kind of clear. We express it as, we decompose it based on the variables. So we take a tree and we only keep those leaves that are labeled by xi, and the other leaf we label it by 0, right? We can do this, and then maybe for illustration, let me add a minus here. And it is fine that you put xi in the front. So now we are really close to apply inductive hypothesis on this tree, except we have minus sign. And what we do is we just take the difference. We express it as the positive part minus the negative part. And then let's like apply the R2 operator on all the trees. But when we apply the R2 operator on such tree, it is equivalent to apply the R1 operator and remove this variable xi. And then we apply the norm operator, the norm here. And whenever we see a summation or a minus, we apply the triangle inequality. And now notice that for this tree, its density is 1, but now we decompose it into 2n subtrees. And here actually by concavity, you can assume that each subtree has density 1 over 2n.
So I'm confused.
Yeah.
P root log 1 over P is a convex function, not a concave function.
No, wait.
P root log 1 over P should be convex.
So this is just like the entropy function.
All right, wait. I'm missing something.
Yeah, so ignoring this square root is just like the entropy function.
Ah, yeah, I'm missing the minus sign. Okay. Right. Okay. So it's convex.
Okay. Well, anyway, so let's just assume that all the 2n subtrees here has density 1 over 2n, and we have in total 2n such subtrees. So therefore, these things can be bounded about by n times like c times 1 over 2n times square root of e over 2 ln e to n. And when you multiply the sum of AI here, what you get is in total, let me just write it here. What you get is just this C square, square root of D over 2 squared, like ln E over P, ln En. And in general, when this is not 2, when you're looking at level L, then this here, it would be like D over L to the L. That reflects D choose L. But the dependence on P will be complicated. And so that's basically what I want to say about this proof. Any questions?
So the induction step from 2 to 3 will be like exactly the same thing, only we'll use the 2 for the for what you have.
Yes. But yes. So if you don't care about like losing logarithmical factor in your upper bound, that's exactly what will happen. I mean, So in reality, I guess in reality, this is not necessarily linear. It can be a degree 2, for example. But what you do is exactly the same.
Yeah. Yeah, so you do exactly the same, but instead of xi, you think of like 2 indices.
Yeah.
Okay. You think of like the product of.
Yes.
Okay. So this is the end of the talk.
Yeah, this is the end of the proof. I don't know what else to talk. Maybe
so maybe just like a recap. So so this is basically the end of the bound for this L.
Can you repeat how the AIs disappeared from this step to this step?
Oh, here, yeah. Here I'm just focusing one tree that all its leaves are labeled by a single
So
word.
that bound of 2n, you're saying for a fixed tree, you get the 2n.
Yes, but it's an upper bound, so all such tree is bounded by that.
I see.
Okay, maybe it's a good time to clap and then see if there are questions.